We are very happy to have Frank Cudek here to have the first speaker session. And he will talk to us about singularities.
Thanks for having me. So the talk will be containing some philosophical and conceptual reflections on the notion of singularity in general relativity, or as in the title, singular structure. That's a bit less loaded term, I think, though we'll talk about that. So I really want to argue for three main claims. So let's get it out there on the table. So first, I'm going to say this: singular structure of space-time, already using the non-loaded term, is best conceptualized as a property of space-time regions, possibly proper ones, of course, not necessarily the whole space-times, witnessed by incomplete curves in that region. Second thing is that which curves witness singular structure is related to what counts as reasonable motion for an observer in general relativity, and hence there is some room for ambiguity because it's vague what counts as reasonable motion for an observer in general relativity. And three, whatever exact definition we choose, whatever kind of curve incompleteness we choose to witness singular structure, being singular will be classified as an extrinsic property. I'll say why. Non-local property, I'll say what I mean by that, and yet a localizable property. And I'm going to also say what that means. And I'll tell you that there is a schema that any such definition instantiates. Okay, there might be bonus material since we have a lot of time, and there might be some extra things you might want to know. There are some technical results concerning what might be considered small singular regions of space-time. Health warning, I'm going to talk only about classical general relativity. So there is, of course, a question of what our view on singularities will be in quantum theory, quantum gravity. I don't know. You're going to have a speaker on that later on in the year, I think. So just hang on. We'll do the classical GR first, and we want to learn about the impact of quantum gravity and singularities. Do it later. But I'm just going to say for now that and the sentiment among physicists that there will be some singularity resolution in quantum gravity is often backed up by not convincing analogies between how quantum physics got rid of singularities in classical mechanics. And there are also some physical arguments, such as Aaron Wall's derivation of something like a singularity theorem in the quantum setting from generalized second law of thermodynamics, which casts doubt on the prevalent sentiment. But I'm not going to say anything more. I'm just focusing on the classical. Yeah. Okay, so the roadmap is this. I'll start with a review of relevant technical facts. Many of you will know many of these things already. If so, relax, enjoy how much you know. Then I'm going to just talk a little bit about adjudicating between different types of curves to choose for a definition of singular structure. Then I'm going to talk about some philosophical stuff, our conceptions of what singular structure is supposed to be. Then I'm going to talk about the notions of locality and localizability of space-time properties. And at the end, I'm going to put my definition schema and talk why singular structure is supposed to be an extrinsic property of space-time. All right. So, possible physical spacetimes in GR are represented by Lorentzian manifolds with the standard mathematical properties, M is four-dimensional, Hausdorff, connected. And G is a Lorentz metric of appropriate signature and so on and so forth, represents the geometry of space, and the meta content can be uniquely reconstructed with the Einstein field equation, so I suppress the stress energy tensor from the models. There are, of course, some subtleties about whether always facts about those mathematical objects correspond to facts about the physical world, but I think for our purposes, we can kind of be ambiguous between space-time, meaning Lorentzian manifold, and a physically possible thing out there. The metric G can be in various senses singular, so there's a familiar distinction between coordinate and manifold singularities, which everyone learns while being presented the Schwarzschild solution that R equals to M is a coordinate singularity. If you change coordinates, then the metric is well behaved at that point. But the R equals 0 is a genuine singularity. There is a curvature scalar that diverges along the curves that go towards what would be points of this value, maybe the Kretschmann scalar. So this distinction is well known. it's not as well known that there are different kinds of curvature singularities, not only connected to curvature scalars. You might have singularities which stem from the components of the Riemann tensor relative to a certain parallelly propagated frame to diverge, even though each curvature scalar is well behaved. And you also might have something like singularities where there's no bad behavior of curvature whatsoever. So, for example, take a Minkowski spacetime, excise a point. Well, every geodesic which would go through that point, actually, there is no point there, so it's incomplete. So it seems that the spacetime is singular, even though it's flat. Now you might say, okay, that's a contrived example, Frank. You just extracted a point from spacetime. This spacetime is extendable. It's isometrically embeddable in another spacetime named Minkowski, and that spacetime is not singular. But there are examples of such spacetimes where they're arguably singular and yet inextendable. So one case is so-called conical Minkowski. If you have Minkowski spacetime, you cut out a wedge of a given azimuthal coordinate, you glue back the edges together. It looks a bit like a cone, but there is, of course, no apex, because then the differential structure would be not well defined. And curves that go towards this apex witness singularities. It's a bit like, a pizza cut into slices. You take one slice and you pretend it's all right by putting it back together. But of course, the shape is no longer perfectly circular, right? There's some kind of thing in the middle that doesn't work out. There are also some plane wave solutions if you don't like these topological things that are also singular, inextendable, and I know to some tastes more physical. Okay, so of course there's a problem that these singularities as points are not really well-defined mathematical points in the manifold. There is no point that corresponds to r equals 0 value in any in the Schwarzschild spacetime. So generally, people say instead of thinking about singularities, I mean, we might talk about singularities vaguely, but a precise definition would only say that a particular spacetime is singular. So singular structure is thought to be a property of spacetimes, and the standard criterion given is that spacetime is singular just in case it contains certain kind of incomplete curve. And then there is some room as to what kind of curves should witness the spacetime being singular. Of course, there's a more fundamental question: how do we even decide which ones are best? Is it just purely intuition, or usefulness in results, or whatnot? I think I endorse the answer that singular structure is supposed to be something that disrupts physically reasonable motion. So there's something in space that I want to say, oh, it's singular. It means that there is some unnatural geometric disruption of physically reasonable motion along the curves that are incomplete in the relevant sense that witnesses those claims about singularity. And those curves, of course, should represent that motion. But the most popular answer is to say that it is not only sufficient, but also necessary that there are incomplete time-like or causal geodesics in space-time that make it singular. So this is the kind of curves that feature in the singularity theorems, Penrose in 1965, the light-like geodesics, or Hawking and Penrose with the time-like geodesics. And incomplete here means of finite affine parameter and without endpoint. Without endpoint means there is no point on the manifold such that there will, for every neighborhood of that point, there will be a parameter value after which there are infinitely many points in the image of that curve for that parameter value that are within the neighborhood. So the problem is, I mean, surely insofar as you want to stay with disruption of physically reasonable motion, that concept extends beyond free fall, which is a kind of motion represented by geodesics. So there are, in fact, geodesically complete spacetimes that yet have incomplete curves of bounded acceleration. And this was something shown by Garrosh. He also shown that different kinds of geodesic incompletes are independent of each other. And it seems that curves of bounded total acceleration represent something like physically reasonable motion, maybe not feasible in some kind of technological sense, but physically reasonable. Okay, so the first alternative is to say, look, the spacetime is singular just in case it contains incomplete causal curves of bounded total acceleration. There is another alternative, which is called B-incompleteness, and it has been quite popular in the early to mid-70s, starting with the word of B.G. Schmidt, and then took up by Hawking and Ellis in their seminal textbook. And this is a bit more relaxed than the bounded acceleration criterion. So the idea behind B-incompleteness is to define a certain kind of parameter for all kinds of continuously differentiable curves, such that it having finite value and the curve having no endpoint would witness singular structure. And the kind of parameter is called generalized affine parameter. And if you, integrate over that parameter, you get generalized affine length. The idea there is you have a curve, you choose a frame, you parallelly propagate it, and then you just integrate over squared components of the tangent vector of that curve relative to that choice of a frame field. Now you might think, well, that depends on which frame I choose, right? Yeah. But it does not depend on which frame you choose, whether that parameter and that length is finite or infinite. And all you care about is whether it's finite or infinite, not about its particular value relative to any particular frame. So you can say that a curve is B-incomplete if and only if it has finite generalized affine length and no endpoint, and the spacetime is B-incomplete if and only if it has any B-incomplete curves. And this is something called like a semi-official definition by Ehrman in his 1995 book, has been taken up by Hawking and Ellis. And of course, the question how to understand this parameter is perhaps best pronounced by comparing it with proper time for time-like curves. So whenever we have finite generalized affine length, we will have finite proper time, but the converse isn't true. So finite proper time implies finite generalized affine length, just in case the acceleration, while not quite bounded, is what I call here Lipschitz bounded, meaning after some proper time, there will be some value L between 0 or 1, such that the growth of acceleration will be offset by the time, the difference between the finite time and the time at that given point being smaller than that value L. So the thought is the growth in acceleration is offset by decrease in remaining lifespan. And you may wonder at this point, okay, what is this B-incompleteness thing about? What was going on here? So why don't just have, I know, arbitrary time-like curves of finite proper time with no endpoint, witnessing singularities, right? Any time-like curve, don't care about acceleration. Well, in Minkowski spacetime, you have time-like curves of finite proper time with no endpoint. You just have to accelerate it fast enough. Say the tangent of tau being your proper time would in fact give you a time of finite proper time and no endpoint. Is Minkowski spacetime singular? You wouldn't want that. You want to have something which doesn't make Minkowski spacetime singular. And surely bounded acceleration does that. But in fact, B-incompleteness does that too. You can prove that Minkowski spacetime is B-complete and therefore not singular according to this criterion. And people like this criterion later because you can define something like a frame bundle over spacetime with a particular kind of metric that people hoped would help you to construct the boundary of spacetime which would contain singularities as points. That project, I think, was misguided. We can talk about that. There are some problems. But the idea of B-completeness is still interesting. Okay, so this is, these are the kind of parameters you might consider. Now is the question, how do I decide between alternatives 1 and 2? Which one is better? Must total acceleration be bounded for physically reasonable motion, or is this weaker Lipschitz bound on its growth sufficient? Maybe you can say, oh, well, if there's unbounded acceleration, I might have infinite energy needed to have this kind of motion trouble, no frame independent definition of energy in GR, either for a point particle or stress energy field. But maybe you can say something like this. Okay, I still might want to have curves of finite integrated acceleration. I have an acceleration vector which I can integrate along the curve. That surely needs to be finite for a physically reasonable motion. And there is an argument for that given by Chakrabarti, Gersh, and Chan-Bin. So they show that if you have a time-orientable space-time, this finite integrated acceleration along the curve is equivalent to existence of some kind of positive bound from below mass function. So there's a mass of the body, and there is a rate of discharge of energy momentum minus mv. V is the tangent vector here along the curve. It's causal and future directed. And also, if you have a causal killing field in your space-time, then that value is finite if and only if the effective energy along that curve, which is the contraction of the killing vector with the tangent vector, is also finite. And they say, look, great, when you look at this, you see that for these spacetimes, there is a sense in which there is energy finite along the curve when you have integrated acceleration. But also, when you have curves of integrated acceleration, they say, they actually do not do weird things in certain spacetimes that otherwise time-like curves could do, like reaching null infinity in Minkowski or arbitrary low value, R value in the Reisner-Nordstrom case or something like that. I'm not super convinced that this is a great argument. So one thing to say about the second point is that you still have some curves of total acceleration that do weird things in space-time. Like in the Gödel space-time, you have closed time-like curves with bounded acceleration. There's an interesting question, what's the bound on that acceleration, but it's another thing. Another thing is that argument which links effective energy to integrated acceleration presupposes a time orientability. Common assumption. Is it fully justified? I don't think this is such a severe problem, but there are some questions you may ask. Was the justification for time orientability either on empirical grounds or some kind of transcendental grounds, let's say? Another thing is, and I think that's more important, is well, generic spacetimes do not have causal killing fields, even locally. The local result is actually quite interesting mathematically, came in like 2005, Rushtilash and collaborators. So you can't really say that this correspondence holds for generic spacetimes, and it strikes me that it's not really a fantastic argument saying that therefore you must consider only curves of finite integrated acceleration to consider physically reasonable function. This might work for just a few spaces. Okay, so this was a kind of review of some relevant technical background. Let's take a step back, consider a more kind of philosophical question. Okay, so right, so what are singularities supposed to be? What's our conception of singularities? I'm using the word singularity. I use the word singular structure. I talked about space-time being singular. So the first kind of distinction is between object and a property, somewhat of a metaphysical distinction. Singularity is a noun, which suggests it denotes an object. Singular structure is a noun phrase that's less certain to denote an object, as we've learned from Frege. And the concept horse is a noun phrase, doesn't denote an object, it denotes a concept horse. I was very puzzled by this for a while, and then set it aside, said, it's a weird thing with natural language. Still generated a lot of literature in philosophy of language. So we shouldn't be misled by ordinary language. Let's talk about singular structure instead. That's the kind of broad term I'm using. And then Ehrman, having this distinction between an object and a property, said, okay, you're going to have two conceptions of singular structure. The nominal, which says singularities are objects. They're not material in the sense that locate in space and time. They're not abstract either in the same sense, numbers are, or sets or whatnot. He quips that they exist with an existential quantifier, meaning our best theory should quantify, which quantifies over all objects in the world, quantifies over space-time singularities. But it didn't say more, really. And then there's the adjectival conception, which says, no, look, there is no such thing as a singularity. That's a misnomer. Really what's going on is that being singular is a property of space-time. Talk about singularities is just loose talk. Okay, so I think great distinction, but we can extend the adjectival conception. So I'll say, look, maybe you should consider the idea that being singular can be property of space-time regions, proper subregions of any given space-time, relative to any particular space-times that they are subregions of. And each represented by some kind of open set, so the whole space-time is a limiting case, so the whole space-time also too can be or not singular. Why? Okay, the first reason is why not? The option to explore. Second reason, which is a bit more serious, is that it meshes with an intuitive idea that in some space-time, some regions are singular and others are not. And physicists sometimes talk that way. So for example, when you have the Kruskal-Schwarzschild space-time here pictured, you might want to say, look, surely the region 1 is not singular, but the region 2 is singular, right? Similarly, when you have Kerr solution, outside the ring singularity, everything is all right. It seems it's non-singular. In fact, there are theorems that prove that if you look at just that region, it's geodesically complete. So there is some precedent in saying singular regions which are proper subregions of space-time, though, of course, not much very clear conceptual thinking about this.
What is
yeah.
region 2? Is the light blue part? Or
It's the light blue part. I mean, this is R equals 0. That's not a part of the manifold.
Saying the region is the part where nothing weird happens.
I mean,
Saying a property of a region, but a region, unless you want to include the singularity as the missing point in the region, any region you want to pick out by itself, right? I think on one of the first slides it said like there needs to be an income. If it's a property of region, it needs to be an incomplete curve in the region, but it will be incomplete in the region itself. I mean,
well, I haven't yet got to what exactly is the definition of a singular region, because the point will be that you have to look at its topological closure to determine whether it contains a witness of singularity that would also be a witness of the whole space-time. So thanks for anticipating the definition, pruning the narrative. That's right. So one might reply, well, there's no clear mathematical criterion for determining whether any given region counts as singular, right? I mean, you can't really say something like, okay, yeah, I mean, just take this region and consider it as a space-time on its own. Any proper region considered as a space-time on its own would be extendable. Every extendable space-time is geodesically incomplete, has an incomplete time like geodesic. So according to any sensible definition of singular space-time, that would be a singular space-time and the region would be singular. So you can't do that. Okay, I agree with this reply. I'm going to say we'll try to amend this soon. There's going to be a definition schema. I mean, thanks for actually ruining the climax, because it's quite elementary. It's not like there's going to be some really some mathematical fireworks going here. And I call this conception the extended adjectival conception of singular structure. I endorse it. That's how people might want to think about singular structure. That it's a property of space-time regions relative to any particular space-time that they are regions of. And you might say, well, on what basis do you say that? What are the kind of considerations that can support one conception over the other? Well, there's availability of mathematical explication, physical fruitfulness, intuitive plausibility, coherence. I think this proposal is at least coherent. Intuitive plausibility, well, I'll try to motivate a little bit with those examples with the Kruskal-Schwarzschild space-time. Physical fruitfulness, up for grabs. Availability of mathematical explication, we're going to talk about this. But I'm going to say also you can make an inference to the best option in a sense by criticizing the other ones. So I'm going to say against the nominal conception as the main contender is to say that there is no decent mathematical explication. There were many attempts to construct the boundary of space-time that would contain so-called singular points. The G boundary of Gerhardt, the B boundary of Schmidt, C boundary of Penrose and others, A boundary, Scott and Chekretz. But there is a general theorem which I think merits the name of a no-go theorem against such constructions, which we might talk about in the Q&A if you're interested. So I take it as a point that there is no decent mathematical explication for the nominal conception. Can't really make mathematical sense of singularities as points in a kind of fully general way that works for all spacetimes, or even all spacetimes of any interest. And the main consideration in favor of the nominal conception, allegedly, is that it's intuitively plausible. So John Ehrman, in this fabulous book, says that the nominal conception is arguably a touchstone of singularities in relativistic physics. Spacetime singularities correspond to missing points. All right, what's the motivation of that behind this assertion? So one thing is that it seems that singular structure is in some sense localizable. You can say, well, there's a kind of singularity there, but not there. Vague speech, I know, but this is basically what kind of data we have now. But I mean, the question is, okay, so what exactly means that it's localizable here rather than there? And is the only available sense, or is the only sense available, is this good sense available only to the nominal conception? I'm going to say, no, actually on this extended adjectival conception, we can also make sense of a singularity being rather there than here, or something. Also, some people want to say we would like to be able to do theoretical physics of the singularity, which seems coherent only when in conjunction with the nominal conception. You'll have a point on the boundary, mathematically well defined. You can check that, I know, geometric or causal or topological properties of that point, neighborhoods of that point, and so on and so forth. And it seems that if you don't go for the nominal conception, you kind of a priori say that's not possible. I'm not convinced by this either, even if there will be some way mathematically of making sense of points in some extended spaces representing something like singularities. It's not immediately clear to me without seeing the details whether that cannot be more carefully interpreted as really representing point-like objects, point-like singularities, rather than idealizations about, limits of smaller and smaller singular spacetime. Okay. So now I'm going to talk a little bit. So I think, to say it again, this extended adjectival conception is the best to think about being singular as a property of spacetime regions. Now you might think, okay, what kind of property is it? And can we really make sense of these claims of, say, localizability of singularities within that conception? So first thing I want to say is let's distinguish two concepts, locality and localizability. These words get thrown a lot in physics, both quantum and classical and relativistic. I'm just going to focus on them as features of spacetime properties. So what is it for a spacetime property to be local? Well, you might want to say there are some formal definitions of what counts as a local property of spacetime, or a spacetime region considered as a spacetime also. One given by Curiel, one given by Manchak, and one given by Krasnikov. I won't necessarily tell you the details, that might not be super important, or the relationships between them. Turns out that Krasnikov and Curiel's definitions are equivalent. They both imply Manchak locality, but the converse is not true. The point is really on all of them, any definition of being singular for spacetime that is based on any kind of curve incompleteness is non-local. Okay, doesn't matter what particularly how they look exactly. Turns out that being singular, non-local property, as one would expect. There are also informal definitions: Butterfield, Lamb, Weatherall. On the first two, where roughly local means associated with a point in spacetime, being singular is clearly non-local. How about the Weatherall definition? Okay, so Weatherall says a property F of spacetimes is local. I call it Weatherall local, just to distinguish between all these locality. If and only if it can be associated with some region of spacetime that is represented by some open set with compact closure. Okay, I set aside relative compactness for now, because the interface of singular structure and relative compactness is a bit messy. We can talk about it in Q&A. So let's just think about what it means for a property to be associated with some region of spacetime. So this is ambiguous actually between A, determinable from the information within that region, that is from region considered as a space on its own, and B, determinable for that region from information possibly beyond that region in a way that is informative and allows distinctions between various regions. Okay, you might be puzzled slightly about this bit which goes after but, right? In a way that is informative and allows distinctions between various regions. This is just a hedge, okay? I say I want distinctions between various regions because I think a definition which says a region of spacetime is singular just in case it's a region of a singular spacetime is pretty bad. So you want to say, okay, in a singular spacetime, this region might be singular, this might not. Also in a way that is informative, so that actually it's not just determinable for any region, whether it is F or not F, but this information might tell you something about the larger region being F or not F. So let's make a comparison. In any spacetime, you can find an open set which is simply connected, and in every spacetime, you can find a set which is not simply connected. Whether you find this one or the other one doesn't tell you anything about whether the whole spacetime is simply connected. Not informative. But I'm going to say, actually, being singular is informative in this sense. If you find a singular region in your spacetime, you know the whole spacetime is singular. Okay? And you can also, we'll see that for every singular spacetime, I mean, it might depend on exactly the definition of singular, but generally you will have both a singular region and a non-singular region. Okay, so I think A, this thing determinable from the region considered as a space on its own, is kind of more like locality. That's fine. But B seems to indicate a different concept. Okay, and I call this concept localizability, right? Plausibly, one can discriminate between regions of a single spacetime that do not exhibit singular structure from those that do. And so you have our previous example, Kruskal-Schwarzschild, region 1, region 2. Region 1, not singular. Region 2, singular. Moreover, identifying a region is a positive test for the whole spacetime to be singular, as I said. So it seems coherent to say that singular structure is a localizable property in this sense, even though it is not local. So insofar as you want to say localizability in some vague sense was an argument for the nominal conception, that is, singularities are objects, not a good argument. There is a sense in which there's a sense you can make of a concept of localizability that captures its, pre-theoretic meaning, as philosophers like to say, which is perfectly consistent with the extended adjectival conception. Okay, seems coherent, not quite is plausible, right? So we need a more precise explication of what it is to associate singular structure to a particular region that vindicates judgments about intuitive cases. So here comes the definition schema. Okay, well, I propose a definition schema for a singular subset of spacetime or a singular region of spacetime. For any relativistic spacetime MG, I say an open psi subset. Psi ranges over desired topological properties of it. U of M is a phi incomplete singular psi subset. Phi ranges over different kinds of curve incompleteness that you might prefer. Bounded acceleration, geodesic, just time-like, maybe causal too, the incompleteness, whatever you want. Is a phi incomplete psi subset of that spacetime if and only if there is a psi incomplete curve whose image is contained in U. So the image is in U, but to check that it is incomplete, i.e. has no endpoint, you have to look at possibly its topological closure. So you need information, unless you're talking about U being actually just M, right? Topological closure of that is still M. But for any open subset, U of M, it will have a non-empty closure because of the Hausdorff condition. So you need to look at the points in that closure to see whether that curve is in fact an incomplete curve. Okay. Okay. So there's a number of virtues for this proposal. The first is very simple. You just look at the curve, which is in the region and incomplete, but to check if it's incomplete, you just have to look outside the region, right? Flexible, yeah, find psi. add your favorites. Classifies intuitive cases correctly. And that's no silly misclassifications as far as I can tell. If you find any, please let me know. So this fixes this kind of physical mathematical challenge to this extended adjectival conception. There is a good sense in which you can say, I have a precise criterion for when a space-time region is singular. Okay. Meshes well with the pluralism about curve incompleteness discussed before. Okay. So it's a definition schema, not quite a definition. Fill it in the way you want. And now we can also say that it also makes precise the idea why being singular is an extrinsic property. So this is some metaphysical jargon. There is a lot of, so caveat. There is a lot of debate in metaphysics how to perfectly make a distinction between the so-called intrinsic and extrinsic properties. The thought behind them is that some properties are intrinsic, internal, within the particular object, whereas some kind of depend on the way other objects might be. So say that my height is my intrinsic property, me being friend of, say, Maciej is an extrinsic property because it depends on the existence of Maciej. I mean, some people have imaginary friends. That's not the point. But I take it kind of first within the mainstream metaphysical literature that it's easier to give examples of extrinsic properties, and I submit being singular is one of them. But also we can just spell this out in a particular framework for the intrinsic-extrinsic distinction given by David Lewis. So this is his reply to a paper by Kim in 1983, where he makes this further distinction between positive extrinsic and just extrinsic properties. So F is positive extrinsic if and only if F's instantiation by any object implies the existence of a distinct contingent object. So you can say S is my proper subregion of spacetime M. If S is singular, then this implies the existence of spacetime points distinct from those that comprise S, namely those which are in the closure. Do I have to admit someone? No, okay. This follows from M's being connected. Sorry. So being singular is positive extrinsic unless one is either A, a necessitist, so believes that necessarily every object necessarily exists, or B, denies that spacetime points in particular exist contingently. If you like A or B, I'm sure there will be another distinction between intrinsic and extrinsic that will satisfy you anyway. But unless you believe in A or B, it seems that in this sense, being singular is positive extrinsic, which is a sufficient condition for being extrinsic for David Lewis. So this is just one particular framework that I wanted to give you to illustrate for those of more metaphysical inclination that indeed being singular is an extrinsic property of spacetime regions, even though it makes intuitive sense just by saying, look, I need to look at the topological closure to know it, right? So it depends on some points that are not in that region, which is exactly the intuition behind extrinsic. Yeah.
We go back to the definition.
Sure.
So where in the definition does this topological closure part come in?
So if it's coming, because it's coming in looking whether that curve gamma is incomplete. Because it's a curve to M. To check if it's incomplete, you check first that it has finite parameter of the relevant kind, and then you check whether it has an endpoint in the manifold. The endpoint might be outside of U. If it will be outside of U, it will be in its topological closure because it's an adherent point to the image of the curve. So this is where you look at points which are not in your original region that you're considering. It's in checking whether this is an incomplete curve.
But these endpoints can really only be either in U or on its boundary.
Yeah.
Or do they always have to be on the boundary?
I mean, no, I mean, you just can have a curve which kind of stops in the middle of your region, right? And you can just have add a point and extend it. Right? But the point is,
Yeah.
if it kind of ends out where the region ends, intuitively speaking, if you look at the topological boundary, that will tell you whether there is an extension or not. So you look at actually very, minimal region of space-time outside to check, at least when you have a positive test. If you have a negative test that you can extend a bit, then you can look farther and farther and farther, right?
So I then suppose you look at the example of Minkowski with the excised point,
Yeah,
and you consider the region, open region around that,
yeah,
and you're not going to add that point back
exactly,
by making a topological closure.
exactly. So this will be a singular region of that space-time. It's a singular space-time, and a region which encloses the what would be the point, which is excised, in fact, will be a singular region precisely because when you take a topological closure, you don't add that point back because topological closure is always taken relatively to your background manifold, and your background manifold doesn't have this point in the first place, right? Is that helpful?
Yeah. So so, yeah.
Good.
The definition of incompleteness you're using here, this stuff that both.
So I talked about extrinsicality a bit, and that's about it. I'm just going to recap now. 3 points that I said in the beginning, which are kind of main claims I'm making. Singular structure of spacetime is best conceptualized as a property of spacetime regions, possibly proper, but in the limiting case, the whole spacetime, witnessed by incomplete curves in that region. Which curves witness singular structure is related to what counts as a reasonable motion for an observer in GR. I must say that thought is not made up by me. It is one of two desiderata for singular structure present in one of Garrosh's papers in 1968, which I just think is right. I didn't say it here in the slides, but in a written document, it's properly acknowledged. And so there's room for ambiguity. Whatever exact definition we choose, being singular will be an extrinsic non-local but localizing property of space-time regions. I try to spell out exactly what I mean by those three features that a property of space-time or space-time regions might have. And there is a schema that any such definition instantiates. So there might be some further questions, and there are some partial answers. I'm going to say, does the definition schema generalize to other space-time theories? Yeah, I mean, nothing in the schema depends on the signature of the metric, for example. It's already about curve incompleteness, which you might define and you might adjudicate between different kinds and different theories. So it doesn't, for example, it doesn't necessarily depend on the metric having Lorentzian signature. But I haven't really explored that question more. Can the definition schema be put to formal work? Is there more than just me giving you an elementary definition? Maybe. There are some results regarding connected B incomplete singular subsets. So one thing I was trying to think about is, okay, if I think that, say, singular regions are given by those B incomplete singular subsets, is it always the case that I can find a region which is in some suitably relevant sense small? So it would add further kind of constraint on this idea of localizability. There is always a small region where you can say that it is singular. There is, of course, a lot of trouble with making sense of small in Lorentzian geometry because there's no distance function defined from the metric. The relative compactness, which is the usual topological condition for smallness, gets a bit messed up when you start, say, excising points. So I have some thoughts about that. We might talk about it in the Q&A. Third question is, okay, how severe are those problems of those boundary constructions where you said, oh, nominal conception, arguably no good mathematical explication, the boundary constructions, they don't work. That's what I said. I think the problems are pretty severe indeed. I mentioned there is a theorem by Garrosh, Walden, Chambin. I think it deserves the title of a no-go theorem. If you're interested in details, we can talk about it. Fourth question is, are there alternative characterizations of singular region of spacetime? I didn't pick up on any those. Well, the answer is not really, but you can think about one inspired by a certain approach by Garrosh and J. Manchak, though they don't endorse that explicitly, of course, nor. How do they compare with the characterization presented here? I think it's less appealing than my proposal, this proposal inspired by Garrosh and Manchak. But again, this is something for the Q&A, perhaps, if you're interested. Okay. Thank you, lieber. Thanks very much.